Okay, so what we have here is comparing diffusion and osmosis. What were the items that we talked about the other day? Jordan, you've got your hand up? Okay, and where do I put that? So if this is diffusion, this is osmosis, and this is transport water. Kylie's table, what's another point we could add? Okay, and that goes for? Okay. So transports water, semi-permeable membrane, this group here. Anything else to add for any area of that Venn diagram? Okay, and so if they both do not require energy, what do we call that? Okay, so let's add that in, if you don't already. Yes. So what we could add there is what Shane just mentioned. This is if it's going from a high concentration to a low concentration. No energy. What then makes diffusion different than osmosis? Okay, so it's not the movement of water. So if it's not the movement of water, it's the movement of particles. Any other differences or similarities that we could find? They're both passive, high to low concentration. One deals with the movement of particles, the other deals with the movement of water through a semi-permeable membrane. Anything else? Good. Okay, let's take a look here. Diffusion and osmosis are examples of what type of transport? Passive. Solutes in water are always trying to move from a high concentration to a low concentration. Now, when we deal with diffusion and osmosis, there's more at play than just things moving, because if you move water into a membrane, inside of a membrane, it's going to get larger. So 3 different types of situations come up: hypertonic, hypotonic, and isotonic. Have you heard of those before? Do you remember back to when we were looking at vocabulary for this unit, and there were pictures up and they had these words? You did look at the situations already. We just didn't have the words for them. So, hypertonic. This is one of those bus trips where you need to stay focused. It's pretty straightforward, but if you chat while I go through a couple key things, then these are going to be confusing. Gentlemen. So, hypertonic. You want to make sure that you realize that we're on hypertonic. The concentration of solutes outside of the cell is greater than that of inside the cell. So solutes from outside try to go in. If there's more solutes outside, the water in the cell wants to go from a high water concentration inside to a low water concentration outside. So the water leaves the cell and the cell shrivels up or gets dehydrated. So in a hypertonic solution, the water goes out of the cell. So the cell will shrink, water goes out would be key things to highlight. So this is trying to show a red blood cell here that's shriveled up. So if we were to draw a picture, so here's a cell, it's in water, but let's say that we've made it a highly salty solution, so this is 40% salt. Yes. Inside the cell, let's say there's a 5% salt solution. So at this point, we're going to look at which way does the water want to go. 5% salt solution inside. So where is there more salt, inside the cell or outside? So there's a higher concentration of the solute outside the cell. So that would mean there is less water outside the cell and more water, or higher concentration of water in the cell.
Is that 5% salt right there?
Yes. The salt or the water? Yes, so according to diffusion, the salt will try to go in. At the same time, though, water is also going to move. Where's the water going to go? Right. There's a higher concentration of water, so we could say there's a 95% water concentration here, if that helps, and a 60% water here. So if there's a high concentration of water inside, it wants to go out. When it does that, what happens to the cell? It shrinks up. So a couple ways that you can look at this. You can say, where is there a higher concentration of solutes? Because you all answered that quite quickly. You said outside. The water wants to dilute the high concentrations of solutes. So if you pick, where is the higher concentration of solute? Water will try to move that way. So that's one way to think about it. A different way to think about it would be, if there's a higher percentage of water in the cell, it will try to go from a high concentration to a low concentration, so it will try to move out to balance the concentrations. One of the ways that I help myself to remember this is, I think if a kid is really, really hyper and they can't sit still, then they probably need to go outside and run around. And if I send them outside to do that, they'll probably run around and get dehydrated. So that's the funny little story I tell myself to remember that the water goes out. So if you need to link it to something, to have a connection to help you reason it out, you can do that. Now, let's flip over the page here. Next type of solution is hypotonic solution. Hypotonic solution means a lower concentration of solutes outside the cell than inside. The solutes inside the cell will try to go out, and the water will try to go into the cell to try to dilute the concentration. And if you have water going in, the cell gets larger. So if we were to draw a picture, here's our cell. This time, let's say there is a 70% salt solution inside. And a 20% salt solution outside. So where is there the highest concentration of solutes? Inside. So where does the water want to go? It wants to go in to dilute that high concentration, right? So water wants to go in to decrease that concentration or balance it out. That's one way to think about how to solve it. The other way would be to say, where is there a high concentration of solute? You said inside. So if there's a high salt inside and a low salt outside, where does the salt want to go? The salt wants out. If there's 70% salt and we said 30% water, and you realize I'm exaggerating the salt concentrations here just to help it make more sense. There's 30% water inside and 80% water outside. Where is there more water, or purer water? It's on the outside. So it wants to go in. Like I said, I've exaggerated the percentages. You'd be dealing with 1 or 2%. So if water goes in, the cell membrane, or the cell is going to get larger. What happens in an animal cell if you keep adding water? It does actually explode. It gets bigger and bigger and bigger, and if it has no way to get rid of that extra water, it will actually break the membrane and destroy the cell. So if you took a red blood cell and you put it in a pure water, distilled water, water would have very low concentration of solutes. There'd be more solutes inside of the cell. The water would go in. That red blood cell would grow larger and larger and larger until it basically explodes. If I put a plant cell in distilled water, there's still more solutes inside of the cell, so the water goes into the plant cell. Would it explode as well? A plant cell has a cell wall. So the cell membrane will get forced right against the cell wall, but it won't be able to go back any further because the cell wall will hold its ground. And it will say the vacuole is full, we can't take any more water in. Okay? But an animal cell doesn't have that option, so it will just break apart. Now, isotonic is what we need to finish up here. So if we know hypertonic and hypotonic, what's isotonic? Equal. Iso meaning an equal exchange. So the concentration of the solute molecules outside is equal to the concentration inside. So water will go out, and water will come in at a balanced rate. Molecules or solutes will go out, and solutes will come in at a balanced rate. Right. Right, and really we could draw another cell, and we could say there's 6% salt here and 6% salt here. So it's the same. If they're the same solution, it's not going to draw the water one way or another. Now, pardon me? It doesn't stay static. It is a dynamic equilibrium, so water from the outside goes in and water in goes out. It just constantly exchanges at an equal rate. Okay? On the next page, here are some examples of application level questions. So with those basic understandings, I want you to start thinking about, why does a plant wilt when it's not watered? Instead of being upright, the plant would start to fall to one side or the other.